Okay, and it is my immense pleasure to introduce today's keynote speaker. So I could do the usual thing. I believe Frank went to college at some point. He might have gotten a degree, et cetera, all the usual stuff. But I thought I'd actually say something a little bit less formal about Frank. You know, we all know that there's this notion of a full stack developer, right? And a full stack developer is somebody who can do like both Java and JavaScript, right? Frank has a rather different view of the stack. Because if you go through Frank's papers, you go through his history, Frank not only knows everything down from the level of bits and packets and things of that nature all the way to category theory. Okay, that is a full stack. All right, and I not just say knows in that he can talk about it. He's got like non-trivial papers, like really amazing papers on it, and he does really great research. I like to think informed by all of his background in theoretical CS and everything else in programming languages, but actually helping us secure the systems that we work with on a daily basis. So it's an immense pleasure to have Frank with us today. Thank you.
Thank you. Thank you so much, Sriram, for that very nice introduction. It's a great honor and a great pleasure for me to be here and have the opportunity to give this talk at UPSA. So thank you, also the audience, for being here. So I want to talk today about confidential computing. And what is confidential computing? Well, it's certainly something that's gathering a bit of industry attention these days. So I have a quote here from Mark Russinovich. He's the CTO of Microsoft Azure, the cloud branch of Microsoft, and he says, confidential computing is set to redefine our expectations of data safety and privacy. That sounds good, right? And it's not just Microsoft. If you look at the Confidential Computing Consortium, that's an organization that promotes the development of this technology, all the big tech companies are there, hardware and software, right? So what is it about? Well, roughly speaking, confidential computing is an umbrella term. It means different things to different people. I'll give my definition later in the talk. But the central idea is we want to protect data while it is being computed on, while it is being used. We want to protect data in use. And this is not only gaining interest in industry as we speak, but it's also something that builds on a very long line of research in system security. I think many of you will recognize at least some of the terms that you see on the slide there. Well, these are all enabling technologies for confidential computing, and they've been worked on in the systems security research community for decades. So there are two big schools, two lines of thought. There's the crypto-based approach to confidential computing, and they say, don't trust anything about the platform on which you want to do your computations. You have to anchor your security in cryptographic assumptions. And then you have to go to techniques like fully homomorphic encryption, secure multi-party computation, and so forth, that are quite performance costly. You'll slow things down. There's a second line of thought, the second school, that's hardware-based confidential computing. And they say, well, maybe you can trust a small part of the platform on which you will be computing. Maybe a small part of the hardware, maybe the CPU package, the chip that actually contains the CPU, maybe you can trust that that is not being under the control of the attacker and so forth. And if you want to do that concession, you can kind of gain a lot in terms of performance. So that's what I want to focus on for this talk. So my scope for this talk will be hardware-based approaches only. So this will be about hardware-based confidential computing. What is confidential computing hardware, and how can we build secure software stacks on it? So that leads me to a structure more or less like this. I will spend quite a bit of time on defining what confidential computing is exactly. So what exactly is the objective here? What do we want to get at? And once we understand that, we look at how to break that objective and then maybe fix it. Right? And one of the key points I want to make, I think in doing fixes, the UPSA community would be very well placed to help, and I'll try to explain that towards the end of the talk. Okay, so what is confidential computing? So I'll actually define what a confidential computing platform is. And a computing platform is very simply something on which you can launch programs. And it will be useful later on, bear with me on that, to split the programs that we want to run in two parts. A public part that contains at least the code, so think of it as a public executable, and then the confidential data that we want to compute on. And if you do that split, then starting a program will take 2 steps. You first launch this public executable, turn it into a process, or you take a virtual machine image and turn it into a virtual machine instance. And then you need to provision it with the confidential data it should compute on. So we split this in 2 steps for reasons that will become clear later. I say program here. What is such a program? So there are actually confidential computing technologies for all kinds of granularities of programs, ranging from a single library, a DLL, all the way to a full virtual machine image. For this talk, it doesn't matter too much. So you can have in your mind an executable launching into a process or a virtual machine image launching into a virtual machine instance, and both mental models are fine. It'll also be useful to have a couple of example programs with confidentiality requirements in mind. I'll use 2 examples that I refer back to a couple of times in the talk. One is a public web server, so very little confidential data, because of course the code is public, Apache for example. All the data, you serve it on the web, so it's public, but you still need, for example, a TLS key to authenticate the domain that you are serving the data on, for example. So you have a small amount of typically cryptographic key data that's very confidential. So preferably not a single bit should leak. And this is representative of a larger class of applications whose main confidential data is cryptographic key material. Then there are other applications who work on big data, and I have as example a medical image processing application that scans medical images for markers for a disease, for example. These work on huge amounts of data, megabytes, gigabytes, terabytes, all sensitive, and medical images are clearly sensitive. But maybe small leaks are fine. If you leak how many images you are processing or the resolution of these images, that's probably fine, right? So the requirements are slightly different for this second class of applications. Okay, keep these 2 examples in mind. I refer back to them every now in the talk. Okay, so now let's look at what a confidential computing platform is, and I'll do that by comparing it to other computing platforms. And I'll start with something we'll use as a baseline too, and the simplest one, a local computing platform. What is that? Well, that is you buying server hardware, installing system software on it, you control the system software, and then you can take your public executable, like your executable file, launch it into a process, and now you need to provision it with its secret data, and in a local system you can just use the file system for that. Everything is trusted here, nothing is attacker controlled. So where does Apache get its TLS key? From a config file on the file system, for example. So you can, using that communication channel, you can give the program its confidential data, and now it can start interacting with clients and servers on the internet, right? So clients visit the website, and the website might call API servers. And in this setting, the typical attack model that we have in mind is we worry that our confidential data might leak to attackers controlling the parties that we interact with or controlling our communication channels, the internet. So a typical attack that's relevant here might be the Heartbleed vulnerability, for instance. If your web server has Heartbleed, well, then maybe one of your clients can get your TLS key by using a buffer overread. That's the kind of threat model we have in mind here. But this is not how we run applications anymore these days. So it's more common to use cloud computing. Maybe your local hardware platform isn't scalable enough, or it's not well managed enough, so you don't want to use it for your critical applications. Instead, when you want to launch your public executable, what you'll do is you'll set up some kind of cryptographic connection to a machine owned by a cloud provider. So this here is intended to represent a cryptographic tunnel, let's say an SSH connection that you make to your cloud provider. And then when you want to launch your public executable, you essentially delegate that launch to system software on the cloud platform, which now turns it into a process or a virtual machine instance. And then you can use this cryptographic tunnel that you set up to also provision your program instance with its confidential data. And so now again, we have a complete program, and it can start interacting with clients and servers. And we still have the same attackers to worry about. And maybe now we also worry about the fact that on a cloud platform, our program will not be the only one running on this system. There may be many other customers running code there, and that's code we don't control. In the local setting, all software on our platform in principle was controlled by us. Well, you can debate about that, but at least in principle. So now we might have attackers here too that try to learn something about our data. The typical attitude here is that this is the responsibility of the cloud provider. It's the system software on the cloud provider that has to make sure that none of the tenants can attack the platform or can attack other customers of the cloud. So we trust the cloud provider and the software that he or that they install to do that for us. And actually we trust the cloud provider and the system software of the cloud for more than that, because it can also see our confidential data, right? So the hypervisor or the operating system here can look into a virtual machine image or a process. It can actually, this cryptographic tunnel will typically terminate at some service running on the cloud platform, so the cloud provider could see our data as it's coming out of the tunnel. So we actually have to trust the cloud provider to not steal our data. Right? And this is something that's concerning sometimes. Maybe you don't trust the country in which the server is located. Maybe the government will kind of put pressure on the cloud provider to get that data and so forth. And so that's what confidential computing is about. Confidential computing is about changing that scenario of cloud computing such that you don't have to trust the cloud provider anymore. You only have to trust the hardware or a small part of the hardware. You don't have to trust who owns the machine, and you don't have to trust the system software on that machine. And the way in which that is done is to change the computing platform a little bit. Now when I want to launch my public executable, I'm actually going to invoke a primitive offered by the hardware of the cloud platform to kind of do a couple of things in a single step. What I want to do is, I want to ask the hardware here to turn this public unprotected executable into a running program instance in a special way. That's why I colored the box dark gray or black now, in a special way such that this program instance cannot be observed anymore by the system software of the cloud provider. Right? How that happens, we'll come back to that, but the idea here is we launch the program. Once it's launched, once we have the virtual machine instance or the process, the system software can't look at the runtime state of this thing anymore. It will know what program is in there because it helped launch it. That's why we kept the program public, but it can't look into the running instance. At the same time, this primitive will set up a cryptographic connection, which is different than the previous one because it now terminates at this black box. Remember, in the previous setting, it terminated at some service provided by the cloud. Now it terminates at this black box. So anything we put in this channel only comes out inside this black box and hence is invisible to the system software. That's another reason why we split the program in a public and a confidential part, because we need a way to authenticate this black box. If I put something in this tunnel, I want to know where it's going to. Well, the guarantee I get from the hardware primitive here is, this is a cryptographic tunnel to a black box running this particular program. So I know this is a black box running Apache, for example. And once I know that, I might be fine with sending my confidential data over, and now it can be loaded into the program instance again. And now we have a running program, and it can start interacting with clients and servers again. And now we can actually consider a wide range of attackers, all the ones we considered before. But in addition, we might start to consider attacks from system software. So how could the cloud provider that we had to trust before, how could that cloud provider attack us, and how can we protect against that? And that is what confidential computing is about. So this is now, in a sense, my definition. A confidential computing platform enables users to launch programs remotely, as I just discussed, with essentially the disappointing security property that no more information leaks than it leaked in the local computing platform. So we don't get any improvement, right? So that's slightly disappointing. On the other hand, the good thing, the strong thing is we get this on a much stronger attacker model, right? So we get this guarantee even if all the software on the platform that runs our code is under control of the attacker. So that's the protection of data in use ID, right? So that's really the definition of confidential computing I want to use. I'm only going to study one aspect in this talk. I'm only going to talk about one aspect. So the creation of this black box is what is typically called the isolation property of confidential computing. And then the second part, you have the creation of this cryptographic channel. This is called the remote attestation, or the attestation part of confidential computing, that I'm not going to talk about. It's also interesting, but we have to choose something. So I want to focus on how is it possible to run programs without looking into them. And This is actually tricky. You have all these technologies, Intel SGX, Intel TDX, ARM, SEV, ARM, CCA, AMD, SEV, and so forth, many complicated technologies, but the key insight is actually not that surprising, it's not that difficult. What the system software does is manage platform resources, allocate memory, take away memory, allocate the CPU to a program, take away the CPU. To do that, it doesn't need to look into the state. It doesn't need to look into the register of a virtual CPU. It doesn't need to look into the memory that it is managing, allocating and deallocating. And once you accept that, actually all that confidential computing hardware does is offer you a hardware implemented primitive to launch a program instance in such a way that it becomes impossible for any software to look into the state of this program instance. That's all it does. And the implementation details vary and are complicated, but they typically just use memory access control implemented in hardware and memory encryption implemented in hardware, and that's it. So we can do this. This is implemented, this is in many commercial systems. So now there is no direct access anymore to the state of this running program, but the question is, isn't there any kind of indirect access possible, right? So the system software might be able to influence or observe these program executions in many other ways that we haven't anticipated yet here. And that's what we want to study now, right? So we want to compare what can leak from a running program in the local computing setting and what can leak from a program in this confidential computing setting, and can we get them to be equal? Because then we achieve the promise of confidential computing. So in order to do that, it will make sense to think a bit more rigorously about what the meaning is of these programs, right? So we will need to model the behavior of this program, and of course, it's a software-based system. You know better than me how to model this, but a traditional, very standard way of doing is to use a transition system defined using operational semantics techniques, and we can do that both for assembly languages and for high-level languages. But that's not enough, of course. An important part of modeling will be modeling the attacker here, right? Because the program will be the same on the local system and on the confidential computing system, so essentially the semantics of the program will be the same. We also need to model what the attacker can do, right? And to do that, what we will do in our models is we will model the power of the attacker in labels on the transition system. Right? So we will assume that whatever is in the state in the transition system is opaque to the attacker. He can't see that. Anything the attacker can observe and influence on the program execution will have to include in labels on the transitions. And it's of course important to get these labels right. If you underestimate what an attacker can observe, then anything we prove based on this model becomes worthless. Right? So I'll come back to that after we looked at a couple of models. So as an example of what that would look like, if we just consider the attacker model of a local platform, wherein at first approximation, the attacker can only provide input to influence the execution, application level input, and see output to observe the execution, then that would look a bit like this. So here is a very simple program. It's a Python program. I assume you can read Python. It manages a list of strings coupled with a Boolean that indicates whether the string is sensitive. So this is sensitive, this is not sensitive. And then clients can interact with it by providing an index, and then if it's a non-sensitive string, they can get the value, and otherwise they get some suitable error message. Right? And then you can see this would be an example transition for a program like that. If we start in this state, the attacker can provide as input index 2. That would point to this entry here. That's a non-sensitive one, so we get into this third case, and we get as output the value B, so the attacker can observe this, and we end in this state here. Right? So this shows that even though states are opaque, values can of course flow to the attacker as soon as the attacker can do some observations. Right? And this is an example of a very direct leak, a very direct flow. Leaks can also be indirect. Here's a very simple example of that. So an attacker can learn whether some sensitive string is present at an index by looking at the corresponding error message. That's a more indirect flow. So if we want to prove that nothing more leaks, we will need to turn to some notion of non-interference. Again, probably familiar, many of you are familiar with that. But I'm not going to prove anything in this talk, so I'll just get away with showing explicit leaks. But if you want to do the proofs, if you go to the papers, you'll see that what you have to prove is a non-interference property, some variant of non-interference. Okay, so now we know what we want to achieve. Let's think about how we could attack this. So what are these influences and observations beyond I/O that an attacker might have? So of course, the most interesting ones to look at are the ones that are caused by the attacker here, right? So we now control the system software. That's what's new in the confidential computing setting. So what does the system software do? As I said, it manages platform resources. So for memory, it will give a private virtual memory address space to programs and map that, typically using page tables, on physical memory. For the CPU, it will allocate a virtual CPU to programs and then use timer interrupts to time share the physical CPU over many virtual CPUs. And this is operating systems 101. So these are the mechanisms we will try to abuse, and when we do that, these attacks are called control channel attacks. So this is using the resource management of the operating system to attack your programs. There are two important classes: page table-based attacks that exploit the virtual memory system, and interrupt-based attacks that essentially exploit the CPU virtualization system. And I'll give you a simple example and then point you to papers for more details. Right? So here's a simple example of a page table attack. To understand it, you need to recall a little bit how address translation works. So the page table is an operating system data structure that provides a mapping from virtual memory addresses to physical memory addresses. And that data structure can be complicated, but we can just think of it as a mapping. Now, there are three ways in which an address translation can go. Right? If a program accesses a virtual memory address, it needs to translate it to a physical address. The first thing that can happen is there's a translation cache, the TLB, the translation look-aside buffer. If the translation is already in the translation cache, the hardware immediately has the physical address, no system software intervenes, and this is great because that means the system software also can't see anything. Right? So if a translation is in the translation cache, that's good for the victim program. But it's not always in the cache, right? Sometimes it's not in the cache, and then we have to consult the page tables. So the hardware will walk the page tables to find the corresponding translation. But the page tables are a system software managed data structure that also has metadata that is modified by the hardware while it's walking the page tables. So as soon as we do that, if we get into the second step, the access in principle becomes visible to system software. Right? There's a third possibility. The hardware can walk the page tables and not find the mapping. The mapping is not defined. And then, of course, what will happen is a page fault exception. Control goes to the operating system, and clearly in that case, the operating system sees the access and can even intervene and do stuff. This is the worst of the three cases, obviously. Yeah. So with that, you should be able to see that by cleverly managing the page tables, system software can see any page access. The simple strategy is always allocate just a single page to the victim program, the one it's currently executing in. And then once it wants to go to a new page, there's a page fault, operating system comes in charge, gives it a new page, takes away the old one, and you continue like that. And then you see all page accesses. This is slightly oversimplified, because in reality, a single instruction can access multiple pages, like a code page and a stack page and a data page, for example, but that's the basic idea. Right? So once we can do that, it's clear that we can leak information, right? And so here's a very simple example how that, for a program like our public web server that wants to protect cryptographic keys, this leakage is definitely bad, right? So here, this is a function used, for example, in RSA cryptography. The details of the function don't matter. This computes a modular power, m to the d mod n, and what is important to know is that this exponent d is then part of the cryptographic key. So this is something we would like to keep secret, right? Now, of course, in the local computation platform, if this function executes, the attacker can't observe anything, and this is fine, right? But now in the confidential computing platform, with these page table attacks, an attacker can see every page we access. Now, if we assume that for this function, the modpow function is on one page, and the two functions that it calls, the square and multiply here, are on other pages, then we can see that you actually learn quite a bit. You don't need to look at the details of this algorithm, but what you have to see is that this algorithm goes over all the bits of the exponent. So the 0 here, the 1 here, the 0 here. And for each of these bits, it will always call square, and if the bit is a 1, it will also call multiply. So for a 0, we will see modpow calling square returning to modpow, which is pages AB being accessed. And for a 1, we will see modpow calling square returning to modpow, calling mult returning to modpow, which is this sequence of pages. And I think it's now pretty obvious that by just looking at the sequence of page accesses, you essentially read off the bits of the key. Right? So clearly for for a cryptographic program that's already too much leakage. And here is an actual measurement. So the toy example on the previous slide was good to see the mechanism, but this is an actual measurement you can do if you use state-of-the-art techniques. This is a picture I took from a paper at Unix Security this year. So what you see on this picture, so this enhances the attack with also using the interrupt power that the operating system has. It will use timer interrupts to make sure that we interrupt the program after every individual machine instruction. And this is tricky to do, but it can be done. I'll point you to papers explaining the attack techniques later. And what you see on this figure here then is, on the x-axis, you see individual machine instructions. So this is a run of a program for about 3,000 machine instructions. And then for every machine instruction, on the y-axis, you see the virtual memory address space. So this is the data section, this is the code section, this is the stack section, right? And for every instruction, we draw a dot for the pages that it accesses. And we see that most instructions access between 1 and 3 pages, right? And so that's the kind of measurement you can do then. And here, this box shows an actual invocation of this modpow function. You see here the code page containing modpow is this page, and we see here plenty of accesses to that code while we are executing the function. We see sometimes a call to square, and sometimes square and multiply. So essentially here, you read off the bits of the key that you're interested in. So clearly too much leakage. Is this also bad for the second class of applications we considered, like image processing, for example? Well, one of the things that the seminal control channel attack paper showed is that yes, the leakage is big enough also for these other classes of applications. So what they showed, for example, is that if you decompress an image that like this, or the original image looks like this, in a confidential computing setting, and then you try to recover that image using the measurements like this one, right? Then what you can reconstruct is what you see here, right? So clearly that's a fair amount of leakage. It's something we might want to worry about. Okay, so that's the basic idea. Here are the papers where you can find more information if you would want to know the details of the attacks. I don't want to go into the details here. Unfortunately, so control channel attacks are perhaps the most relevant ones for confidential computing, but certainly not the only ones. All the other attacks that we already knew before we had confidential computing, like microarchitectural side channel attacks, where you monitor the cache to learn what memory addresses a program is accessing, or speculative execution attacks where you influence the speculation behavior of a processor to learn about what a program is doing, or power analysis attacks where power consumption by the CPU tells you something about the data the CPU is processing, or memory safety attacks even where buffer overreads and buffer overrides allow you to read program state and influence program state. All these attacks become typically more powerful if you control system software. Because, for example, manipulating the cache will be easier to do for software at the highest privilege level than for a user level program. And it's interesting if we think about all these attacks. Well, here is the stack that Sriram was referring to in his introduction. The way we build systems is by layering abstractions on top of one another, right? So we compile a structured language like Rust into a user-level instruction set architecture like RISC-V plus system calls, and the operating system implements the system calls using privileged instructions, and all these instructions are implemented in a processor described in Verilog, for example, which is compiled to a technology like CMOS or something like that. And if we now put all the attacks I talked about on this stack of abstraction layers, we see that they're all over the place. Memory safety exists because of the way the compiler is treating undefined behavior. Control channel attacks that we just discussed exist because of the way the operating system manages resources. Right? Microarchitectural attacks like the cache attacks and the speculative execution attacks, they exist because of the performance enhancements we implement in processors. Power analysis attacks exist because of the way CMOS transistors work. They consume power at the point where they flip bit, and so forth and so forth. So this should make you a bit pessimistic on how to defend against this, how to solve this, right? Actually, an argument I'll make is this probably means that to fix this, we also need to do fixes across all these abstraction layers. We probably can't fix this efficiently just at the top layer or just at the bottom layer. That'll be one of my main points when we talk about defenses. Okay, so let's look at defenses now. So if we want to design defenses and prove them secure, then we need models that incorporate all these attacks that I mentioned. So we need these label transition models that I mentioned, but we want to have in the labels the influence and observations that all these attacks that I mentioned give the attacker that controls system software. I'm going to give you two examples of such models, one old and simple one and one that's a bit newer. So the old and simple one is the constant time leakage model. That's maybe a model that at least some of you will have heard from. So this is a very useful model, an over-approximation, but a relatively tight over-approximation of the information that an attacker can learn through control channel and microarchitectural side channel attacks like cache attacks. So what this model does is, okay, we see all these complicated attacks. Essentially what they can learn is what memory addresses you are accessing. So let's just admit that the attacker, whenever the program accesses a memory address, the attacker can observe the memory address. And as a consequence of the fact that code is also in memory, this means the attacker can also see the control flow, because we will read instructions from memory too, so we know the program counter, so we know the control flow. And sometimes we consider other leaks, but for this talk I'll just consider these two. So if we add that as observations on our labels, we have modeled all these complicated attacks in a very simple way. That's the power of the constant time leakage model. And now we can try to write our software in such a way that secrets don't leak, even if we do these additional outputs to the attacker. And that's what constant time programming does. So a constant time program makes sure that it doesn't leak its secrets, even if we have all these additional observations. And modern crypto always, at least aims to be constant time. There are still many vulnerabilities where they miss cases, but the goal of most modern crypto libraries is to actually be constant time. So let's build this into a model of a simple assembly language. I do that because I will build on that assembly language later to also model other attacks. So this is a very simple programming language model, right? So we have a finite set of registers, we compute on natural numbers, we allow in the assembly language arbitrary expressions so that we don't need too many instructions. We then only need 6 types of instructions. So this is a computation of an expression and assigning it to a register. This is loading and storing from memory. This is an unconditional jump, and this is branch if 0, branch if equal to 0, so a conditional jump. And then a program is just a list of instructions, and here you see how you could compile some pseudocode into this assembly language. This is standard compilation, right? The state of such a program would be what you expect. It's a memory, a register bank, and the current value of the program counter. That's the full program state. And then we can build the transitions. We can define an operational semantics for this. Again, you know better how to do this than me. So for example, if we start in a state like this, where memory has values 5 and 4 at addresses 0 and 1, and all registers 0, then what this program would do is compute 5 plus 4, right? It would compute the sum of the 2 elements in the array A starting at address 0. So the first step would be, we fetch this instruction, we check whether I is smaller than 2, it is, so that's a true, so a 1. So R0 becomes 1 and the program counter becomes 1. And in addition, the constant time leakage model says we should give the program counter to the attacker. Right? Same for the second instruction. And for the third one, when we do load our first array element here, this is a data load. So the address that we load from here is A plus I, which is 0. Right? So we tell the attacker, okay, we're loading from address 0. Because the attacker could learn that jumping through many hoops using a control channel or a cache attack, but let's just admit that it leaks. Okay? So, and we can continue doing that until the end of the program. So the nice thing about the constant time leakage model is that it's so simple. It only needs observations, and it's actually it's a bit over-approximative, but tight enough that we can actually still usefully work with it. So it's a very powerful and useful model. But the big downside is it doesn't model all the attacks we discussed. In particular, speculative execution attacks are not covered by the constant time leakage model, right? And these are important enough that we want to care about them in the confidential cloud computing setting. So just as a quick reminder, before I add this to the model, what are speculative execution attacks? Well, they exploit the fact that modern high performance processors, they don't fetch an instruction, execute it, fetch an instruction, execute it, like we did in the semantics on the previous slide. What they do is they fetch a bunch of instructions, 100 instructions in a reorder buffer, and while they're fetching them, they may have to speculate on the control flow, because if you reach a branch, you don't know whether it will go left or right, so you guess it will go left and fetch instructions from there. And once you have a bunch of instructions in the reorder buffer, you can execute them in any order that makes sense. Whenever an instruction's dependencies are satisfied, you can execute it. You still taking into account that you want to commit the effects of the instruction on registers and memory in program order to the architectural state, to the memory and the register bank. Right? So that's the basic idea of an out-of-order processor. Now, on such a processor, an attacker can still observe this constant time leakage, right? So we still have the same leakage as we had in the previous model, but the attacker can do more, because an out-of-order processor has to make all kinds of choices. How many instructions will I fetch? Will I predict the branch to go left or right? Which instruction in the reorder buffer will I execute first, right? So there's all kinds of choices that a processor must make, and these are made by heuristics implemented in the processor, and unfortunately, these heuristics are influenceable by an attacker controlling the system software. For example, an attacker could train a branch predictor to get used to the fact that the branch always goes left, and then the predictor will also predict for a victim program that the branch will go left. So we also have to model this influence of the attacker on the execution now. And one way to do that is by allowing the attacker to provide what are called directives to the processor. So whenever the processor has to make a choice that's made by heuristics in the processor, we actually give the attacker the choice to resolve the outcome of that decision, right? So I'm going to explain how that works, how we can extend our assembly language model to handle these things by walking you through the famous Spectre v1 attack. Right? So what is Spectre v1? I assume most of you will have seen this somewhere, but let me briefly walk you through it. So this is the typical piece of code vulnerable to Spectre v1. So what we have here is an array read under a bounds check. Right? So we have here an array A of length 2. And under a bounds check, we read from it, and we know that the values in A are public. We don't care that they leak. So once we read R0 here, we don't care that we use it as an address, for example, later, which might leak it to an attacker to the constant time leakage model. We don't care because we know we're not reading a secret here. We do a bounds checked read from a public array. Right? However, on an out-of-order processor, this branch might be misspeculated, and we might actually be reading out of bounds speculatively, and then we can actually leak this value, right? That's Spectre v1. So let's show this on this model with directives. So here we have again the state of our processor now extended. We have the register bank here before and memory as before, but now we extend it with a reorder buffer of in-flight instructions that's initially empty. So we need to extend the program state a bit. So now the processor has to choose how many instructions will I fetch. And if I fetch many, what will I do with this branch? Will I predict it to be taken or not? Well, we allow the attacker to do that. So the attacker provides influence here, right? Label on the transition. It says fetch 3 instructions, and then for this branch, predict that it will go to address 3, so it will not be taken, and then fetch 2 more instructions. And the consequence of that is that we will have in the reorder buffer all these instructions. Right? Don't mind the details. I'm not going to discuss the full formal model here, but that's the basic idea. Right? The next thing that the processor can do is execute some of these instructions. And again, several choices are possible. You could first execute this, or you could also already execute this. Right? So again, we let the attacker choose. The attacker says, execute this third instruction first. Yeah? And now we see, well, I actually was out of bounds here. And what we're actually reading here is this secret that somewhere else in memory that this program isn't even talking about. Right? So we see that this happens. We also leak the fact that we access address 3, but that's not a bad thing yet. The bad thing is we have actually gotten the secret in our processor, and now the attacker can say, now execute this instruction, and this will actually leak this secret value because we're now using it as an address, and now the attacker has the secret value in memory. So this shows that by having these additional influences and the additional state of the reorder buffer in the model, we now actually model microarchitectural side channel attacks, control channel attacks, and speculative execution attacks in this assembly language model. So these are the kinds of models on which we want to build our defenses. Right? Okay, an interesting question here is, when is such a model correct, right? And that's actually tricky. So we should validate it in at least 2 ways. So first, the semantics should be functionally correct. It should behave as RISC-V, right? But that's a classic problem. If you build an operational semantics, you have to test it against the actual language that you're modeling. I remember a paper from Sriram, The Essence of JavaScript, so many years ago, doing exactly that. This is known stuff. But we need correctness here also in another sense. We need the attacker model to be correct. We need to have a correct model of attacker capabilities. And this is much harder to validate. So what we want to check here, the one-line summary is, whenever an attack that we want to consider, an in-scope attack, can distinguish 2 executions on the actual system, then these executions should also be distinguishable in the model. And this is trickier because distinguishing these 2 executions in the actual system might require quite a bit of ingenuity from the attacker, and so it's much harder to test this. Actually, I believe that the only way to build good models like this is to have attack research. So people with an attacker mindset should try to do these things, and once we understand what the power of attacks are, then we can try to come up with models like this. Okay, so based on these models, we can now start thinking about defenses. And as I said, when I mapped all these attacks on the tower of abstraction layers, it's unlikely that we will be able to defend against this by just changing the hardware or by just doing something in the programming language. So what I think is more likely is that to obtain both efficient and secure design, if you don't care about performance, we can do it. I mean, you can just use a very simple old processor that doesn't share any resources, and many of these attacks go away. But if you care about performance and security, we probably have to do smart things in all the layers of the stack. Yeah? Just as a hand-wavy example, at the programming language level, we could use a security type system, as the PL community has studied for many years. Then a compiler could deal with the microarchitecture side channel attacks by turning the code into constant time code, maybe doing control flow linearization and data flow linearization. And then we could handle maybe speculative execution attacks in the processor by doing tail tracking of secrets in the process. Very hand-wavy. So we have 3 mechanisms that work in concert to get a nice end-to-end security property. Actually, in their Turing Award lecture, Hennessy and Patterson, the 2 famous computer architects, they predicted that this kind of vertically integrated design will be instrumental for performance in the years to come. And they mention on the side, and likely also for security. So I completely agree with that. So this will be essential to get a combination of performance and security. Right? And I think this is actually the reason why I'm giving this talk at Uppsala. I think doing this is what you guys at Uppsala are good at. This is about integrating mitigations like type systems or runtime checks or tail tracking at multiple layers of abstractions and having kind of modularity in the sense that you want contracts between the layers. You want to know what guarantee you get from the previous layer when you're building the layer on top. And that's exactly what this community is good at. And I think this design space of coming up with defenses that you spread over these layers and that you coordinate well, this design space is huge. And I want to give 1 or 2 examples, depending on how I'm doing on time, from things that we did in our group. There are examples from other groups, but we only scratched the surface here. So if you're looking for a good problem space to work on, where you can apply your systems and programming languages expertise, and that's the PSL in Uppsala, I think. I think this is a great area to look at. Okay? So I'm going to give you a couple of examples just so that you have an idea what this might look like. Right? The first example is a paper from Usenix Security 2 years ago. It's called Prospect, and it's a hardware-software co-design, so it only works on 2 layers that deals with speculative execution attacks that I just explained. So that's why it's a good example to give here. I'm just going to explain how it works by going again over the Spectre v1 attack that we just saw. So what Prospect asks at the software level is, it uses essentially constant time programming as the mitigation there. So Prospect requires code to be constant time, but Spectre v1 snippet is constant time, right? It doesn't even touch secrets, so it's definitely constant time. So second, software should inform the hardware where secrets are. So you should, for example, tag memory whenever it contains a secret. There are more efficient implementation techniques, but conceptually that's what you do. You should make sure not to have a secret in memory unless that memory cell is marked. It's okay to do some overmarking, but you shouldn't have secrets that are not marked in memory. Why do we do that? Because now when the processor is executing code, whenever it loads
something from memory into the reorder buffer, into the microarchitecture, into the processor, it will know it's a secret. And it can taint track that secret throughout the reorder buffer. So when we compute on it and forward values to later instructions, we will know which values have been influenced by secret. And then the final thing, and that's the actual mitigation then, that Prospect does is, whenever there is a potentially dangerous instruction, like loading from an address, that is tainted, the countermeasure will take away this choice. The processor will not do that anymore, and hence we reduce the influence that the attacker has essentially. He can no longer ask to execute this instruction, and so the problem goes away, because at some point the misspeculation, you can't execute this while it's speculative, and it's a misspeculation, so at some point the speculation will go away, it will be squashed, and the problem is gone. Make sense? So you see very simple mitigation in hardware, very simple existing mitigation in software, which is good because crypto is already constant time, and the two working together give us now the guarantee that the code running on an out-of-order processor doesn't leak any of its secrets. And we have in the paper a full proof of that. We have an implementation on out-of-order RISC-V core and a bunch of experiments. I just want to mention one thing. I don't want to fully explain the experimental evaluation here, but I want to make this point that by doing this cleverly, you can get security and efficiency. And what we get for Prospect is, if you do the marking of secrets precisely, then we don't have any performance cost. And you can even see that analytically. So we measured it experimentally, that's what the table does, and I'm going to point you to the paper for that. But even analytically, you can see that this must be true, because when do we block a speculation? So we block a speculation when a secret is about to leak, right? Now, blocking a speculation can cost you performance, but it doesn't cost you performance if it's a misspeculation. And if an instruction is about to leak a secret, for constant time code, that must be a misspeculation, because constant time code will never architecturally, non-speculatively leak secrets, right? So there you see that, again, the combination of the IDs is chosen to make sure that we keep our performance, right? So that's the challenge of doing these kinds of vertically integrated design. Let me do one final example, and then I'll wrap up. So a second example, published at Usenix Security this year, is TL Blur. It's again a hardware-software co-design, so we do something at the hardware level, something at the software level, and this protects against the page table attack that I mentioned a bit earlier in the talk. So what does TL Blur need at the hardware level? The hardware needs to provide a mechanism where a confidential program can ask the hardware, call a handler in the confidential program whenever the operating system returns to me. So if there's an interrupt and the resumption, the confidential program must be able to be guaranteed that the handler will be called. Right? This is useful because the operating system is the attacker, so essentially when we come back from the attacker, we get a chance to do something, to implement a defense. And actually many possible defense strategies are possible there, and I'll explain one. Now, this hardware extension, we're fortunate enough to work together with Intel to get this in one of Intel's confidential computing technologies. That's in Intel SGX, the AX Notify extension. So this is available on actual commercial systems. So this is an attack we can immediately, defense we can immediately deploy, essentially. So how does it work? So recall the page table attack. So essentially what the operating system was doing here is trying to determine every page that you access. And remember I said, if an address translation is in the translation cache, it becomes invisible to the operating system. So the operating system will try to keep the TLB, the translation cache, empty, and it will do that by frequently going back and forth between the victim program and the operating system, because the TLB gets flushed on each of these transitions, right? So what TL Blur does is it uses this handler, the fact that it can intervene every time the operating system returns, to prefetch the TLB with all the pages it expects that will be accessed. And then all these accesses will be invisible. So a simple heuristic is to just instrument a program to remember all pages it has accessed in the past, right? We call that the working set. And then the handler will prefetch all these pages whenever you resume from the operating system. And the consequence of that is that all the operating system can still see is whenever you touch a page you haven't ever touched before. And that's an enormous reduction in information. So here you see the measurement I explained a bit earlier in the talk, right? So this is what you can still usefully measure once you implement TL Blur, even without remembering all the pages you accessed, because that's of course not realistic. You keep a small working set of recently accessed pages. You see that the amount of information that leaks goes down tremendously, from 3,000 to about 200 useful measurements. And you see that where here you could read off the key bits directly, here you can only see when the first time you touch a 1 bit, essentially, right? So maybe for crypto, maybe for the web server example, this is still too much. But for this image processing, this reduces the leakage to a point where it's not useful anymore to an attacker. So if this was an original image, this is what we could reconstruct, and this is what you can still reconstruct with the defense in place. You can still find the dimensions of the image, for example, but you can't reconstruct anything useful. Okay, so these are 2 examples. As a conclusion of the talk, what I hope I convinced you that this confidential computing area is a treasure trove of research challenges. You can do very interesting, challenging, intellectually nice attacks here, and you can do very interesting, challenging, intellectually difficult and nice defenses here. In particular, I hope that I convince you that this idea of vertically integrated design, where you like do multiple things at multiple layers in a well-coordinated way, is promising, and I hope you will consider looking at that with the expertise that you have. I think programming language expertise, formal methods expertise that is in the UPSA community is essential to this. If you want to do this, I just want to mention that especially if you want to do hardware-software co-design, for years now we have been in the process of setting up an open source ecosystem of tools to help doing that. We have our own open source RISC-V core. We have both an in-order and an out-of-order implementation of it, and it's designed to allow easy extension with security extensions. We have now used it in about 5 or 6 papers. Some other groups have used it. We are trying to kind of build a community around this so that doing experimental work on this is a lot of work, a lot of implementation work. And if we can share some of that effort, that would be great. And so now we have the core implementation, and we have tools around it to do performance measurements, to do security evaluations. We're working towards an extensible compiler and so forth. And if we can get the community to work together on this, we will be able to explore this design space so much more efficiently. So if you're interested to look at that and want to work with it, don't hesitate to reach out. The main developer is very happy to assist people who want to get started with this. And with that, I think my time's up, so I have to wrap up here.
The mics are open. As you can see, F stands for Frank and also for full stack. So.
Ben Titzer, Carnegie Mellon. So this question might sound like I got you, but I promise you it's not. So one thing that I've learned about side channels is that they're outside of models. So when we add a side channel to a model, then we can prove that we've mitigated it. But there's a long list of them. And so a lot of vulnerabilities have started to show up. There's a long tail of them. I'm curious what you're thinking, what the long-term strategy for that is.
Yeah, great question. Thank you. So clearly, you're right. I agree with everything you said. And the way to manage this is by having an attacker-defender race, right? So yes, side channels will never stop. I mean, you can't have provable security in the real world. This is impossible. But what we can have is we can understand which of these side channels have what kind of power, and that's what attack research is about. So people should do empirical attack research. Say, if I own a cloud machine and I have this program running on, what can I do to it? And then only the attacks that are impressive enough, we model them, we take them in our models, and then we can reason on this. And maybe, of course, somebody 5 years from now comes up with another ingenious idea and finds another attack. That's unavoidable. I mean, we don't ever expect security to be done. This will never be the case. But we need to manage this in a kind of risk management style way. But that's why it's essential to have a combination of people with attack expertise, and I think the system security has that, actually too much of it maybe. But you need people with kind of defensive engineering skills for the other side. And it would be great to have some kind of competition between the security crowd and the formal methods crowd to kind of, a bit like the crypto community has these competitions about cryptographers and cryptanalysts. That's how we should handle this, in my opinion. I don't know if that answers your question, but...
No, thanks, that's great.
Yeah.
Hi. So in this model of initializing a remote process such that even the OS doesn't have access to everything about it. So in this model, the setting up part is still done via the OS. Yep. So if that part is evil, can it not just pretend to me that it has set up a secure enclave for my process?
Yeah, great question. I should maybe have emphasized that more. I'm going to go back to the picture. That's where the attestation that I didn't talk about comes in, right? So at the point where you do this setup, right? It's true. Maybe so. I'm sending this public executable. I'm sending Apache. Nothing prevents the cloud provider from bugging Apache, from putting all kinds of evil things in there, and then launching that. But remember that I said, you launch it, and you also get this cryptographic channel to this black box, and the guarantee you get what the hardware will measure what the operating system launches. It will measure the identity of the code. What exactly is the code that is running there? And I know the code I want to run, and I get a cryptographic guarantee that about the code that is running in the black box. And if it's not the code I expected, if any bit of it has changed, I will refuse to send my data. But if it's exactly Apache as I sent it, then I am willing to send my data and get that guarantee. So essentially, I'm saying the code is the identity. In practice, it's a cryptographic hash of the code that is authenticated. So you know if the operating system would cheat, the attestation part would fail. If the operating system doesn't cheat, you have the guarantee that in the black box exactly your Apache is running and not a bugged version.
You still have the problem that like you're not communicating with the remote system by, like you're not attaching alligator clips to the legs of the CPU or the pins of the CPU. So anything you hear back from, including this, like, you give me an executable and I just give you the hash of it. But
remember, we trust a small part of the hardware. So we trust the CPU package. And so the CPU package is involved in the loading process. So the operating system has to ask the CPU in steps, for example. So here is the first page of Apache. Here is the second page. And the hardware, the trusted part of the hardware will measure this. And will say in the end, okay, I have created this black box. I have now filled it with these bits. I have measured the bits that I put in the black box. And now I will set up a cryptographic channel showing to whoever did the launch that this is what's in the box. So that's where we need to trust. If you don't want to trust the processor, if you don't want to trust the hardware, we need to go to homomorphic encryption style solutions. But this is what you win if you trust a small part of the hardware. Yeah, does that make sense?
Yeah. Thank you.
Thank you.
Okay, I had actually the same question, but now I have a follow-up. So what hinders how do you not know that the cloud platform basically emulates a CPU and like a malicious CPU?
Yeah.
You can't know that, right?
Yeah. Very good question. So there, cryptography is used to assure that. So when Intel makes a chip, or when AMD or ARM makes a chip with confidential computing technology, they embed a cryptographic secret in that chip. And so you need to use a kind of a public key infrastructure to be sure you're talking to a genuine CPU. And the idea is that the CPU package is so complex that getting that key out is undoable. And if you would want to emulate the behavior of the trusted part of the CPU, you would need to get such a key out. Actually, attacks, so one of the attacks our group did, one of the first attacks that completely broke Intel's first trusted computing technology was getting this key out. Once you get this key out, it's game over, right? So, and then they have a kind of a recovery mechanism where they upgrade keys and things work again. But that's the idea. So the trusted hardware part is initially preloaded with a secret known only by the hardware manufacturer, and the hardware manufacturer can attest that the cryptographic channel that's being set up is actually set up by a genuine Intel CPU. If the cloud provider can get that cryptographic secret out, it's game over. Yeah.
Okay, thank you.
Yeah.
Hi, Frederick, Nokia Bell Labs. A follow-up question to that. I'm pretty sure you're aware of the bad RAM work from some of your colleagues. Can you give your perspective on there, where they also try to attack basically the hardware threat assumption?
So some of the confidential computing technologies give guarantees not only against all system software, but they say even some parts of the hardware can be attacker controlled. Yeah, and okay, let me say this bad RAM work that that you refer to. So the idea of that work is, what if the cloud provider with physical access to the machine kind of puts a man in the middle between the CPU and RAM, right? Then that gives you even more attacker power than what I discussed here, right? And some of the confidential computing technologies claim to defend against that too. And so what that work did is showing that with a relatively cheap technique, you don't need a full man in the middle, you can kind of remap memory using tricks by lying to the processor about size of memory chips and so forth. And they show that with I think a $50 attack, they can actually break some of the confidential computing techniques. So I didn't talk about that because I considered software-only attacks. But if this is a question, should we consider attacks like this in scope? Yes or no? Well, I think we should actually.
Do you see that as a part of the hardware-software co-design?
I think this is something that probably can be solved in hardware. Okay. Well, maybe not. So the problem. Good question. So the problem doing memory protection well is hard if you want to support large chunks of memory. Encryption is easy, but integrity protection is expensive. Actually, the very first confidential computing technologies had better memory protection and weren't victim to this bad RAM attack. Later, when they wanted to support full virtual machines, they weakened the memory protection a bit, and then they became more vulnerable to these kinds of attacks. So maybe a hardware-software co-design where a program says, this is absolutely critical memory, and I have a special malloc that allows me to malloc memory that will then be cryptographically encrypted and integrity protected, but another malloc that can be bigger chunks, but you get less protection, might actually make sense. But then, I haven't thought this through, but you see that you have the security performance trade-off there, and we can only solve it by indeed looking at the multiple layers. So yes, thank you. That's actually a good suggestion, I think, to consider this. Yeah.
Okay, thanks.
I guess I'll use my privilege to ask the last question. Throughout your talk, as you've been talking about your models, I've been trying to think about the experience of trying to do these proofs, right? And it feels absolutely overwhelming because the amount of non-determinism that your attacker models have, I mean, that's what they have, of course. Are there lessons for us as people who do proofs about programs? Do you sort of restrict yourself to a small set of attacks each time? Because then, I think you get the question I'm getting at. Like, are there disciplines you have learned from doing this so many times that we could learn from about how to do this kind of modeling and proof?
Yeah, a very good point. So coming up, this is the million-dollar question, right? So finding the right abstraction that gives you something simple, but that covers enough of the problem space is just so difficult. And the constant time leakage model was a great example of that until it was not expressive enough anymore. And I don't think we have something yet that's as good as the constant time leakage model in terms of elegance. I think the constant time leakage model was okay to do. I mean, people have done machine-checked proofs with that. The people from INRIA, Gilles Bart and others have done that. So I don't think we have models of that kind of elegance and abstractness while at the same time covering enough ground for all the attacks yet. But I think this is what the PL people are good at, sure. Finding good abstractions.
Because I think like in crypto, right, the Dole-Evian model, I mean, obviously doesn't cover everything, but it's such a beautiful model. It's so easy to capture a formalism, and it gets you so far. And I think maybe we're still more in infancy in the hardware setting for that sort of thing.
That's a good comparison, actually. Some of the proofs we do feel more like in computational crypto, where you have to do back translations, whereas it would be nice to find the right abstraction so that you can do this well. But that's the million-dollar question.
So I think on that note of challenge to the community, we should thank you again.